In the next sections, we'll have Kun Loganathan Ravisanker, Associate Technologies and Business Development Directors, Southeast Asia, presents how Dow advanced safety and circularities of rubberized surfaces through innovations and value chain partnerships. With a track record over 22 years of product developments and market implementations in the specialties, chemical, and consumer good industry under his belt, it has a deep appreciation for value chain cooperations and engaging academic institutions to promote sustainability from his technology leadership role in China and Singapore. In his current role, he has responsible for developing new market and technology partnership strategies and executions in key growth countries with ASEAN. What innovations and policies is used to enhance sustainability in this case, we will know in a minute. And again, if you have any queries, please feel free to drop yours in the chat box during the presentations. Then we will come up with the Q&A sections. Moreover, to have a query view, please click the view buttons and select side-by-side presenter mode. Thank you. On these occasions, please welcome Kun Loganathan.
Hi, Ms. Faye, thank you very much for the introduction. I hope you can hear me okay. Hope everybody in the line can hear me okay. Good afternoon, good morning. So I assume, yeah, okay, good. You all can hear me. I'm very honored to be part of this international technology and science conference. You know, it's my great pleasure to be here today. And, you know, if you can go to the next slide, I think I can control myself. Okay, I can control myself. Yeah, sorry. Okay. So, you know, in the speech so far, you heard about, you know, how, especially from our packaging colleagues, you heard about how Dow uses our innovation capabilities, right, in developing sustainable solutions that addresses some of the pressing challenges in the world, right? So, and also they talked about, you know, to use the reuse, recycle, reduce approach, you know, as part of the circular economy approach, again, to solve the similar issues that we just talked about, right? So my presentation today is along the same lines, but I'm going to be talking a little bit different from the plastics and focus more on the rubber aspects of the material science, right? And also specific the construction industry in this presentation. So the presentation will be two parts. The first part would be how we have identified a problem in the rubberized sports surface industry that is mostly because of the use of solvent-based adhesive that is causing a lot of safety and the environmental issues, and how our Dow scientists were able to develop a water-based acrylic copolymer technology that is a alternate substitute for this current solvent-based technology. On the second part, I also talk about how various players in the value chain come together for one common goal of promoting circular economy, especially in taking some of those used rubber shoes that we throw away to back into the communities in the form of, you know, rubberized sports surfaces. So these two parts combine in a way. They talked about the same story, but there are two parts. At the end of the day, our goal is to improve the safety profile of those such rubberized sports surfaces. So before I go to some of the technical aspects, I just wanted to show you how the innovation process works in large product and material science companies like Dow. You know, you can see here there are many steps involved, ideation all the way to implementing some of these new technologies that you develop, right? Many different functions gets involved. At the beginning of this process, normally it's going to be marketing and R&D that comes together, take some ideas, and then start putting some concepts and you know, prototypes together, and then validate them multiple times, and then eventually go to feasibility demonstration, right? And then other functions within the organization comes in, you know, could be the process, the scale up, you know, our manufacturing teams would come in to ensure that this technology that we are talking about can be scaled up to commercial scale, right? And eventually the sales organization comes in and then take these products and solutions that we develop, go to the market and generate revenue for the companies. So, and on the bottom, I also listed many measurements that we follow. You know, as an organization, as a company, obviously we want to generate more revenue through innovation, right? I think that's one of the objectives for us. And you can measure that through how much percentage of your sales come from innovation, right? That's very common metric, but you can also see along the whole process, we have multiple other measurements. For example, you can measure how much patents that you generate, through when you ideate a new solution, how much of those patents really lead to a commercial success and contribute to higher returns on the investment that you do. So there are many measurements that we take. I think today my key point here is, in this process, it is very important that especially when you are trying to address a safety, sustainability issue, it is important to ensure we have the product safety, product stewardship, we call it in an organization. They get involved and ensure that we have many measurements that we put in place to ensure that product that we develop is safe and sustainable. And we also, take that and verify externally through third-party labs before we go to the customer. So I think that is very important in this set. So that's what I want to highlight. So the ideas can come from anywhere, right? Normally our ideas come from our customers. So that's the starting point. Everything starts from our customers. But also, you observe the market trends, some performance improvements, some futures that come in, all those contribute to ideas. But there is another category of ideas we look at. One is some of the critical sustainability aspects, health and safety aspects that can also lead to potential ideation that eventually can lead to new product and that can generate not just economic value, but also it helps with enhancing the sustainability aspect of those products and technologies in that industry, right? So moving on. Sorry. Okay. My mouse is a little sensitive. Here we go. So let's start with the rubberized surfaces, right? There are different types of rubberized surfaces, including the running tracks, that you may see in your schools and in your communities, in stadiums, the oval shape, that's a typical rubberized surface, sports surface, right? But there are many other kinds as well. And normally these rubberized surfaces, are all site applied. There are one more kind that is, prefabricated system, like a roll sheet. You can bring it and install it in the field. But majority of the systems, are done in situ, meaning applied on site, right? How do they do that? They basically combine rubber granules and then with an adhesive put together, and then they would apply on the site and create those nice looking surfaces, right? Typical practice in the market is, use a lot of solvent-based adhesive. Two-component polyurethanes are one of the normally used adhesives. They are proven. They have excellent performance characteristics. But also, what happens on the downside, this leads to a lot of VOCs, volatile organic compounds. Sometimes some of the catalysts that they use can be based on the heavy metals. So there are a lot of hazardous substances that can come off from those surfaces over a period of time, and that could cause some issues, right? In China, we have seen that, back in 16, suddenly there are a bunch of school kids got very sick playing in such surfaces, especially in hot summer days. And that the investigation led to eventually pointing, use of hazardous materials in those rubberized surfaces. And then that led to many stringent standards now that are coming up in China, in many other countries as well, limiting the amount of hazardous substances in those rubberized surfaces, right? So in this presentation first part of the presentation is all about how our Dow scientists were able to pick on this challenge and then come up with a, acrylic water-based adhesive technology that is eventually a sustainable replacement, safe replacement for those, solvent-based adhesive solutions, yeah. Just to give you a little bit more on, how those rubberized materials look like, you can, to start with on the left side, you can see here, there are multiple layers, but most of the systems that we deal with are normally 2 layers, sometimes 3 layers, but, we don't need to go too detail, for just for this discussion, we can start with a 2-layer. So the bottom would be based on these SBR rubber, styrene butadiene rubber from the recycled automotive tires, those black rubbers in the range of anywhere from 2 to 4 mm, a little bit bigger. And they are then bound together by an adhesive and then they are applied on site, right? On top of that, you have EPDM-based rubber granules. Why do we use EPDM granules? Obviously, they give you a very nice appearance, right? Good color, bright colors. They also protect the SBR beneath, because SBR tend to be UV sensitive. The temperature tolerance is not that high, but EPDM can provide that protection for that, right? And these EPDM particles are normally a little bit smaller, finer, and based on this different thickness, use different adhesive dosage or level, if you will, to bind these things together, and then they cure on site, right? So that's the typical structure. And on the right side, I've listed many different rubberized surfaces. On the top, you can see those running tracks that you commonly see in your schools and stadiums. There are many different types, obviously, depending on where you use. If you go to a school, the permeable type is normally a 2-layer. What it means is permeable, the water can easily go through, so you can start playing immediately after a rain, right? So, but if you go down the line, there are different types. If you go to a Olympic stadium, national stadium, they may use a different layer, like solid layers, sandwich systems. The system configuration is different. They use much more adhesives, and they are higher performing, right? And that defines the durability and performance level of some of these surfaces. And then you also have playgrounds. If you go to your condominiums or your community play areas, you will see those colorful rubberized playgrounds. And these playgrounds are normally, again, similar structure. Top layer would be with multiple EPDM granules, different colors, and then base layer would be basically a SBR black rubber, right? Again, bind together by some of these adhesives we just talked about. The running track that I put in up on the top, the thickness can be anywhere from 13, 15 mm. In that, the base layer would be about 10 mm, and then the top layer would be 2 to 3 mm or 3 to 4 mm. So around that ballpark. The playgrounds can be a lot thicker, anywhere from 20 mm to all the way to 130, 140 mm. Just because, if you look at these playgrounds, you have multiple play equipment, right? The kids say sliders, you have those climbing structures and all. So we have to ensure that there is a very good protection. If the kids fall down, from the height, you want to have the protection, and normally you achieve that through much thicker structure and standards. There are many standards, especially EN standard, that defines what type of thickness based on the height of equipment that you use, right? And then you also have sports court. Most of the sports court, like tennis court, badminton, volleyball, you see them. They're normally very hard, cement, concrete based, and then they're painted with some coating. But there are also rubberized surfaces, especially if you want to create them for some, elderly communities or for kids. You also have softer courts, and you may see them around. And again, the structure is very similar, but just that, it may have multiple layers based on what type of sports court that you deal with. Yeah. So we talked about the rubber, rubber SBR, EPDM, we talked about that. The next component, as I said, is the adhesive, right? Conventional adhesives are the polyurethane solvent-based adhesives that are not safe. So for us to develop a alternate, safer solution, you need to understand the requirements. So here are some of the key requirements from the adhesive point of view. Obviously, you started off with making sure that your adhesive is safe. So that is your key. You have to define specific requirements around that. And then you also want to make sure that the bonding strength between the adhesive component and the rubbers are very good, right? You want to hold those rubbers together for a really long time, right? The life of that rubberized surface. You also want to make sure that cost doesn't go too high. It has to be similar to what you are doing in the market today. It has to be durable, obviously, right? So those are all the critical things that a customer would expect. But when you create a new adhesive technology and then you look at internally, our manufacturing colleagues would say, hey, make sure it is not something very different that I cannot use my existing infrastructure to produce. So it has to be aligned to your current asset footprint, right? Obviously. On the installation side, this is where things get a little trickier. You can imagine installers have been doing this for a long time. They're used to a certain way of doing things, right? They use certain tools. They want it to be done within a few days so they can go and do another project in somewhere else. So they want it to be done on the timeline that they're used to. So some flexibility is there, but you cannot expect them to take longer time. So those are things we need to address, right? When you develop a new adhesive technology. And then on the performance side, you have to ensure your solution meets out of the two components. You can imagine rubber, adhesive. So both contribute to the performances. So you need to, although your rubber is fixed, you need to ensure that the adhesive component you design is going to ensure that you meet all those performance standards that are out there for such surfaces, right? Typical requirements should include, you're talking about a rubberized surface for safety of protect the athlete. So it has to have good force reduction. So if you fall down, you are fine. It has to have good deformation. It has to have good toughness and elongation, elasticity. More so, it should also have good slide resistance, right? When you slide, you don't run, you don't want to fall down, right? So it has to be have good slide resistance as well, right? So in this adhesive development process, if you look at the conventional solutions, you can start on the right side. I talked about the 2KPU being one of the common adhesive solutions, right? So you can imagine there are PDI-based, MDI-based isocyanates, right? And then you have formulated polyol, and at the job site, the workers should mix together, and then along with the rubber, and then they will cast it on a concrete or a typical substrate based on bitumen, right? And then the polyurethane linkages starts forming. They are rigid, cross-linked. You have good rigidity and flexibility comes from that structure of the urethane. It has a very good bonding with rubber, so you get a very good performance, proven for a long time. You go back 1960s, 50s, such systems have been in use, so it has a very long track record. Then in the recent past, you also see more and more one component ready-to-use polyurethane comes in, right? So these are again a NCO terminated pre-polymer, right? And then you also have some monomers, isocyanate monomer. They're mixed together. But when you further mix it with the rubber and apply it on the side, they would take the moisture from the atmosphere, and then they're going to start reacting, start setting, and give you that similar rigidity that you talked about earlier, right? Ambient conditions obviously play a role, but more so the catalyst that they use in the formulation, the chain extenders, etc. They also play a role in that reactive setting time, if you will, right? And this is where again the trouble starts. Sometimes some of the heavy metal based catalysts can be a concern for safety, right? So that's what we are trying to address. On the left side, when we attempt to develop a water-based adhesive, to understand the curing mechanism, before you find a solution, you need to understand the curing mechanism. So if you look at the curing, it normally starts off with polymer particles coming together, densely packing first, right? When the water evaporates, they start packing together, and then they continue to kind of flocculate. They become much more compact in nature, and as temperature reaches above that minimum film formation temperature of the polymer that you design, they will further deform. And eventually what happens, in phase 3, they will start forming partial film. This is where what happens, the polymer particles come together, and then there is some small water within the polymer particles. We call it interstitial water that starts evaporating. And then that kind of forces those particles to further, deform and come together. In the process, the polymer particles will start diffusing out of the particles, the polymer chains, right? And then they'll start intermingle, entangle with each other. Eventually, they form a complete polymer film, right? And this polymer films would then hold those polymer particles and give you that bonding that you require. So it is very critical that you understand that. So this by the system that you deal with much thicker system, we talked about 10, 15 mm thicker. So you need to ensure that you design the polymer composition, the monomer composition to achieve the right TG, use the formulation know-how with right coalescence to kind of bring down the minimum film formation temperature so you can achieve that curing that you want in a shorter period of time, right? So when we started this design work, the initial formal polymer designs were pretty bad. They didn't cure at all. Obviously, they are not designed for that purpose, but eventually we continued to optimize polymer composition and formulation, and we're able to get to the level that we really wanted to be. Just to show you some pictures, the formulation also, polymer is one part, the formulation plays a critical role, especially, you are dealing with a lot of very hydrophobic monomers, so you need to have a good wetting. So, the adhesives can spread very well around the rubber granules and then create that interlocking. When they cure, they kind of lock with those, uneven surfaces you see on the rubber granules, right? And then create that mechanical locking. So that contributes to the bonding that you seek, right? And then also by playing with the functional groups in the polymer and also with some of the cross-linking chemistry that is in our toolbox, we were able to create a very complex interpenetrable network, IPN if you want to call it. Those network within the polymer particles can further enhance the cohesion between the polymer particles, improve the toughness, improve some of the strength properties that we need for this application, right? Eventually, we also realized that there is some strong chemical interaction from the acrylic polymer functional groups, and also these rubber granules would have certain functional groups like mercaptans, for example. So there is a certain level of interaction, and then that leads to better bonding, improved addition that we need. We can also adjust the formulation, polymer chain back, the backbone to enhance the curing profile that we need. Just show you another picture of the microscopic picture. You can see here the polymer film in the white here. That's the polymer film. It sits very nicely. Cured polymer film sits nicely between the EPDM rubber and the black rubber in a two-layer structure. I showed earlier. And these polymer films, they strongly again, mechanically interlock, and also there is a chemical interaction that leads to some of the desired physical properties, bonding that we need, and also the curing speed, right? Eventually, that's what I just want to share here. I also don't want to claim that acrylic copolymers equals to polyurethane. It's not. Polyurethanes are polyurethanes. The strength properties you can achieve with polyurethane design is really significant. But at certain applications, you could, by designing a right level of polymer composition and formulation, you can achieve the properties that you require for that specific application. And that's what we have done in this specific rubberized sports surfaces we're talking about, right? We have done a lot of testing against many standards. You can see here, we have tested it against the Athletics Federation that manages all the running tracks, type of surfaces. We have tested against the Tennis Federation requirements, badminton requirements, even some of the European standards like CE. So we know we can meet the requirements of the typical performance requirements that are expected out of these surfaces, right? And also, we have the real projects. We're talking about 4-lane running track, 8-lane running track, large surfaces based on this type of binder technology. Goes back to 2014-15. So we have a very strong track record to prove that this new binder technology that is water-based acrylics can provide that type of durability that you seek. Yeah. So in a nutshell, I just wanted to share that we have a new water-based technology that goes under the brand name EcoGround. You can see here, it has advantages in multiple steps in the value chain, right? As a user like you and I, it is safe, very low odor, it is free of hazardous materials like free TDA, MDA, etc. So it is safe. So that's what we set out to do, and we did. The other benefits we also realized is, being a water-based system, the workers are very happy with that because, solvent-based systems, you need to clean, you need, again, more solvents to clean. So it leads to more odor, potential exposure to hazardous substances, right? So here you can just clean with water. So that's an advantage. For the project owner, like, school building owners, governments who build those infrastructure, for them, it opens a much larger installation window. Typically, if you are working on a school, you want to make sure that you complete this in a school holidays, summer holidays, because of the odor and then the VOCs that you generate. But with water-based systems, you can do it anytime. You can do it over weekend and finish the project, and students would not even see a difference. It would be brand new, right? Anyway, this technology is now recognized globally. We have received the R&D 100 award in 2017 This is one of the well-recognized program in the material science world, so we are very happy with that. In the next part of the presentation, I have a few more slides, so please bear with me. We'll wrap up soon. Here, I talk about how many players in the value chain, especially in the rubberized sports surface value chain, come together to be able to come up with a solution to replace SBR and also repurpose the shoes that we normally throw away, right? So that thereby promote the circular economy concept and reduce the CO2 emissions. So this part of the presentation is all about that. Start with the shoe rubber. Why shoe rubber, you ask? We consume so much shoes. That is a fact. I don't have statistics for the global level, but at least in Singapore, that where I am based at, we buy more than 220 million shoes a year for a population of 4.5 something million people. So you can imagine we buy a lot of shoes and we also throw a lot of shoes away that goes into landfill, incineration, and then leads to CO2 emissions. So can we find a way to reduce that, right? So that's the concept there. The SBR rubber that we talked about, right, from the recycled tires, again, that there is circular element there, but unfortunately, there are also safety concerns from those rubbers. A lot of studies show that they are potentially hazardous, and more standards coming out now to try to push the boundary to limit the hazard materials in such rubber materials. So in a way, what we are looking for is to see if we can replace those rubber with another circular material, thereby reducing the CO2 emissions, right? Just to show you at the higher level process now, this idea came up when Dow team has been talking to Sports Singapore. Sports Singapore is the extended arm of the Sports Ministry of Singapore. They manage all the sports infrastructure in Singapore. So when we had this discussion, we said, yeah, we can attempt that. And as our technical team were able to take some shoes and pull together and then tested it. And we realized, it is possible to use those rubber from shoe to be used in such applications. So we wanted to test it at large scale, make a trial, if you will, like a feasibility at large scale. So we quickly formed a project team from both sides and put together some funding. And we started engaging the communities around that area where we wanted to do the demonstration. So we asked schools and some of the residents around there to donate their shoes that they otherwise throw away. And they were happy to donate a lot of shoes. So the next step was to have one of the universities come in and then say, okay, how do you take those shoes and convert it into granules, right? At the end of the day, we use small rubber granules. The SBR, if you remember, it's about 2 to 4 mm size, different shapes, but the size is around that ballpark. So how do you get to that shape, clean, right, shape that we desire? So they've done some work and come up with mechanical grinding as a feasible option that is cost effective and simple also, right? But the issue was at that time, we didn't have anybody in Singapore who could do that on a large scale. We are talking about in thousands of kilograms, right? Not just few pairs. And so that's where we had to go to Malaysia because, again, to go to Malaysia, we are taking waste material to another country. That is a major issue now. These days, you probably can see in the news, transporting waste is a major concern. So, however, with government involvement, we were able to solve those issues with a commitment that we would not even drop a single waste in Malaysia. We'll bring everything back into Singapore. So that's the commitment, and we did that. And eventually, we were able to do a small project as a jogging track that you can see in the picture below, which is built as part of a football stadium that is coming up in Singapore, which will be used by international tournaments, right? So big athletes would come and use this track to warm up before they go and play the football in the football ground. Some more information here. You can see here, collect shoes. You have to mechanically split, grind, sieve them to clean, and then convert them into granules. And then eventually they became a rubberized surface, right? I also wanted to know that, as a shoe rubber, they are fairly lower in density. You are dealing with multiple shoe components, right? Different brands have different densities. So it's hard to really achieve a desired performance every time consistently. So what we ended up doing for such tracks is to kind of combine some SBR. We couldn't really do 100% sure rubber right away. So we had to go with a 50 split. So we achieved that desired toughness, rigidity that it required from the base layer, right, from the SBR. So we didn't want to compromise the performance as well. So we had to do a split, but we also later realized that some of the softer surfaces like playgrounds, you could really push the boundary and go even very higher level of shoe granules in such surfaces. Yeah. Some more information here. You can see at the top left, you see a bare substrate, a concrete base, a long jogging lane, and then you start applying the base layer. The application here is very manual because it's not a large surface. But if you are looking at a 8-line running track in the big stadium, that requires a specific machine. But for small areas, typically it can be done with manual application. You can see here the much more zoomed out picture of combination of shoe rubber plus some SBR. So you can see black and white combination there. And then on top of that, you come and apply as EPDM. Again, like I said, EPDM gives you that aesthetics protection for the base layer, right? And then the right picture shows you the complete finished track. So in a summary, you can see here, in 2019, this was just an idea. We wanted to test it out. We collected about 21,000 pairs of around 8 metric ton of shoes. A lot of school kids came forward and donated. Like I said, some of the universities helped us to identify the conversion process. And then in 2020, we expanded that. We have done more projects, playgrounds and such, collected more than 75,000 pairs. And then now in 2021, we were able to work together with multiple government agencies, right? Buy a new machine. Our customer here has committed to using that machine that is funded by the government partially. So it's in a way, it's a private-public partnership, right? And our customer has been able to take these shoes and then grind them into rubber granules, right? We have more than 130 in many different areas, schools, universities, even stadiums, shops like Decathlon, they all help us with that. In summary, you can see here, we wanted to show you that, health and safety issue can be one of the innovation driver for you. You can create not only economic benefit, but you can also address some of the safety issues and sustainability issues through innovation. I want to highlight again that, if you really want to promote circular economy, recycling type of initiative, it is very, very important that everybody in the value chain come together. You cannot do it alone. Dow cannot do it alone. And universities, many of you are from schools, so you play a critical role, and so are the community. So that's the only way to achieve that circular economy, right? We are very glad to show that, we were able to replace a solvent-based adhesive technology that is very hazardous with a very clean, safe, water-based acrylic copolymer technology, that has already, so far it has proven to work well. Last but not least, we were also able to improve the safety profile of the rubberized surfaces by replacing some of the SBR with, shoe rubbers that would otherwise end up in, landfills. So I'll stop here and happy to take any questions you may have. Thank you for the opportunity, and I hope this presentation helped you to inspire to do more around circular economy and then innovate more green and sustainable materials in your work. So thank you again.
Yeah, thank you very much, Kun Loganathan. So there are some questions from the audience, and let's start with the first questions. So please comment about the lifetimes or endurance about the rubberized sport surface compared to the typical surface from solvent-based adhesive technologies. Yeah, so the normal surfaces, the life would be anywhere from 8 to 10 years, around that 10 years mark. And normally you have to replace or renovate. So in the project that I just discussed, right, we have case studies going all the way back to 2014. So, we know we have history of more than 7 years by now. So that gives us confidence that such systems can work for 8 to 10 years easily. So we don't see any issue with the durability of such water-based adhesive. Yeah. So for the second questions, for the can you choose road, since it's mix of mixed brand, mixed qualities, or even mixed lifetimes of shoe bottom rubber, how to ensure that the road materials is homogeneous and non-slippery?
Yeah, so that's a good question. So if you see that the shoe and then the black rubber that we talked extensively, that falls on the bottom layer. So you really don't come in contact with that layer. Then the top layer is normally based on the EPDM. So you design such a way that the coefficient of friction, right? The slip resistance is pretty high. There are standards for that. We have to meet around 47 BPN, like British pendulum number. That can be converted into coefficient of friction through some tables that we have. So typically, if you achieve around 47, 50 plus, I think you are pretty confident that you won't slip and fall on that surfaces, even if they are wet, right? You also don't want to go very high. If you're going to 60, 70 BPN, that means it's too rough. If you fall down, you can damage your skin. So you have to design such a way that it is around that standard that they have set. Yeah.
Okay. So for the third questions, can other rubber-based products such as like car ties or natural rubber pillow be used instead of the shoes?
Yeah, I mean, we already see in China now, our colleagues are already working on, there are bicycle tires. Those bicycle tires are based on polyurethane. They are not based on the SBR rubbers. They are basically PU foams. And they are now taking that and recycling it back into such rubberized surfaces. So it is possible. So there are many ways you could do that. Certainly, this is what we want. We want ideas like that. We want people to attempt to do instead of throwing materials away, find ways to recycle them back. So certainly, it is possible.
Yeah. So for the next questions, what should be the next potential materials instead of the shoes?
Yeah, like I said, for a such rubberized application, you want good cushioning, right? You want that protection for if you fall down. So anything that has that cushioning, rubbery nature, cushioning effect, that can be repurposed into rubberized surfaces. So, or even in some of the textiles and that are softer in nature, they all can be considered as part of potentially as a alternate.
Okay. So due to the time limitations, we have to apologize that we can't respond all the queries. However, we will be contact you to answer the questions via email as soon as possible.
Yeah, I'll be happy to do that. Yeah, thank you again for the opportunity.
Thank you very much, Kun Loganathan.